simplicial complexes. So this picture here shows a sphere, one of the most basic examples that we deal with in algebraic topology. But to calculate various kinds of topological invariants of the sphere, it's convenient to kind of divide it up into simplices. In this case, it's going to be like triangles and just edges and vertices. So there's various ways we can do that. So if we just look here, so here we've divided the sphere up into 8 patches, and each patch is essentially a triangle, but it's a bent triangle with bent edges. And this is kind of in an octahedral pattern, and then we can flatten everything out. Okay, so now we've got an octahedron. So in some sense this is equivalent to the sphere, but we need a bunch of formal definitions to explain exactly what kind of equivalence we're talking about. And so here we've got this pattern of 8 triangles, and we can calculate various topological invariants using that decomposition. But that's not the only way we could try and divide the sphere into triangles. I mean, here's another way. I mean, of course, there's infinitely many different ways, but here's just one other example. We can divide it into a kind of football pattern, sort of icosahedron with 20 triangles like this. Okay, so here we've divided the same sphere into 20 triangles, and again, we can flatten it out. So here's another decomposition into triangles, and we could use this decomposition to calculate various other topological invariants again. But there's no kind of obvious guarantee that if we start doing calculations with this decomposition, that we're going to get the same answer as we got with the octahedral decomposition. I mean, that actually turns out to be true for the main invariants that we're going to be interested in. But that's not so easy to prove. That's going to be quite a chunk of the work of the course. Yeah, so the tasks we need to do, we need formal definitions. What exactly is the relationship between the sphere and the octahedron and the icosahedron? And we need to prove various things about how you, various kinds of questions you can ask, where you're going to get the same answer if you try and analyze them using the octahedron or using the icosahedron. Here's another little example of spaces divided into simplices. Okay, so here we've just taken a triangle and we've divided it up into 1, 2, 3, 4, 5 different simplices like this. And now we can sort of modify this by we can just slide the vertices around, and then as we slide the vertices, then we just keep the straight edges and straight triangles, so everything else follows along as we just move the vertices. And so this illustrates the fact that we can, by sliding the vertices, we can just turn the triangle into a square. So that's one way of saying that the triangle is kind of essentially the same thing as a square. This is kind of quite a sort of rigid and combinatorial way of doing it, because everything is with triangles and straight lines. There are also kind of more flexible notions in terms of homeomorphism and things, where you can have an arbitrary kind of function from the square to the triangle, provided it's bijective and map and its inverse are continuous. But that's another group of ideas that we're going to need to explore. One other little thing I'm going to mention, I mean, this is not just pure mathematics. This whole idea of decomposing spaces into triangles and tetrahedra and edges like this is actually kind of computationally very useful for solving partial differential equations in science and engineering. So here's a little example of that. The phrase that's typically used in engineering is finite element models. So here we've got a finite element model of a cylindrical magnetic shield, and you would use this kind of decomposition to calculate the magnetic field equations and understand what's going on in this machine.